Differential equations. We're on lesson 7.4, day 2. We are on the third page. We're actually on example 6. And this is what we're talking about. We were looking at convolutions, and you could have an equation, just like so. F of t equals 2t minus 4, and you've got this integral. Now, ironically, this is not a differential equation. If you're looking real quickly here at that, we can still apply LaPlace transforms to be able to solve for f of t, because we have f of t on the left side, but it's also on that right side. So I guess the very first thing that we could take a look at, I've highlighted this in yellow. You can notice that that integral really is a convolution. We could say, this is f of t minus 2t minus 4, and 4 times, and we could say that's the sine of t convolution with f of t. We have it written out in with respect with that dummy variable of tau. But what we're going to do to solve this is actually apply a LaPlace transform everywhere. And it's only going to take a moment. In fact, what you can do, even with this 2 right here, you can pull the 2 out and just worry about the LaPlace transform of the t. Here you have a minus 4, and we've got that LaPlace transform of this convolution. Now, that theorem that we talked about earlier is really, really nice. It's going to help us with the convolution. Obviously, we've got the Laplace transform as capital F of s. The Laplace transform of t to the first, well, it's going to be 1 factorial all over s to the second. And then we'll have our minus 4, but right here now we're going to have a multiplication of the Laplace transforms. This is the sine of t as I apply the Laplace transform. My k is 1. I'll have k over s squared plus k squared, but again, my k is 1. And the Laplace transform for f of t is capital F of s. And you can see right here things have, in fact, cleaned up nicely. They are, in fact, getting quite a bit nicer. I'm going to multiply everything by that denominator of s squared plus 1. And as I do that, the left side will have s squared plus 1 times capital F of s. This fraction will have 2s squared plus 1. We'll have an s squared plus 1 up on top. We've got this s squared down below. And the s squared right here is just going to cancel out. You'll have a minus 4 capital F of s. I'm going to bring my s terms, capital F of s terms on the left side. We'll have s squared plus 1 capital F of s plus a 4 capital F of s. And then on this right-hand side, of course, we'll have 2. And we could even distribute that to 2s squared plus 2 all over s squared. And as we factor out an f of s from both of these, you'll have an s squared plus 1, and then also this plus 4. I hope you can see that the 1 and the 4 are the like terms. You'll have s squared plus 5 when we clean this all up. So here's our 2s squared plus 2 all over s squared. Let's continue this up here in the top right corner. What you can do solving for f of s now, we'll have our 2 s squared plus 2, but then down below we're going to have our s squared. And we're also going to have an s squared plus 5. And it's right here where, you want to use your TI-89 to expand. I'm not going to take the time to type that in and go step by step, but hopefully you're going to be able to follow on your own and get this to work out. As you do expand, you'll get 8/5 times 1 all over s squared plus 5. I did that off to the side on my own. And then this would be 2/5. You can see what I'm doing. I'm putting a little bit of an edge on that s. Very, very tricky to confuse the s and a 5. Well, you might guess what we're going to do next. We're going to do an inverse Laplace transform everywhere. And as we do that, first off, you'll notice that this s squared plus 5, really we don't have an s up on top, and we know this is going to be related to sine, but we're going to need to have a k in the numerator. So I'm going to have this 8 over 5. So as I'm doing this inverse Laplace transform, hopefully you can see that it's radical 5 squared down below. Your k, in other words, is radical 5. That means I need a radical 5 up on top, but then I'm going to have to counterbalance that by putting a radical 5 down below. Here we can say we'll just pull out our 2/5 and do an inverse transform of 1 over s squared. Well, the inverse transform of capital F of s is your little f of t. But here, like we said, hopefully you're noticing that, this is actually the sine of kt. So that's the sine of radical 5t. And the inverse transform of 1 over s squared, I hope you are familiar with, that is a t. And that, by the way, is going to be our final answer. And it's a little f. Okay, I'm going to finish up right here with the integral-differential equation. This really is a differential equation. And just want to point out to you that Laplace transforms are definitely going to be used. So I'm going to do a Laplace transform of y prime. And then I'll have 6 times the Laplace transform of y. But right here, pulling out a 9, I just want you to realize that really this is y of tau times a 1. This is the convolution of y and 1. You can definitely think of it that way. And I think that helps significantly. So let's think about this. Is we take our Laplace transform of y prime. You can see it's a first derivative, so I'll only have s to the first. That's s, capital F of s, minus f of 0, plus, well, the Laplace transform of y right here will be capital F of s. And here we go with our convolution. We know that the Laplace transform of 1 is 1 over s, and the Laplace transform of y would be a capital function of, f of s. So we'll have our f of s all over s, but then, of course, we have a 9 right here. Right-hand side, the Laplace transform of 1, you just get 1 over s. And once again, maybe it's a good habit to just put some extra edges on your s so you do not mistake it for a 5. By the way, you also know that y of 0 is 0. Now at this point, I'm noticing that my denominators have an s, so I'm going to multiply everything by s. And I think that's going to help out quite a bit. We'll have s squared, capital F of s. This would be 6s, capital F of s. Here we're going to get just a 9, capital F of s. And the right side, of course, we're just going to have a 1. And now what? Well, we can factor out an f of s from this, and you'll be left with s squared plus 6s plus 9, which, by the way, I hope you're going to be able to quickly see this factors. And it factors, guys, into s plus 3 quantity squared. And at this point, we're close to being done. Well, say our capital F of s is equal to 1 over s plus 3 quantity squared. So how do we finish? Well, we're going to go ahead and do an inverse transform now. And we'll take our inverse transform of capital F of s. We'll take our inverse transform of 1 all over s plus 3 quantity squared. And hopefully you're noticing that, over here we'll have our, f of t. But as we're really paying attention here, you might remember this is going back to our first translation theorem. You might realize that this is going to be the inverse transform of 1 over s squared, but we're going to have s get transformed to s plus 3. That's really what happened here. So once again, we can say, what is this inverse transform of 1 over s plus 3 quantity squared? Well, it's going to be so using that first translation theorem, if we apply our Laplace transform of 1 over s squared, we would just get a t. But remember, we have to have e to the at. Also, our a here would be -3. So that's going to be e to the -3t times t. And that's what your f of t is going to equal. So that was actually our first translation theorem. And amazingly, then we are done.